Section 12.5, Superconductors. So you know that a conductor is a conductor of electricity. That's what you're talking about with a conductor. So you could also have conductors of heat. But right now we're talking about electricity, conductivity of electricity. And a superconductor is not one that does it better necessarily. It's that there's no friction. So if you could imagine running through a swimming pool up to your waist, okay? Run through a swimming pool with no water in it, it's easy. Run through a swimming pool with water in it, it's harder. Run through a swimming pool full of sand, and it's almost impossible. So what'll happen is that electron is running through that wire. It is running along the edge of the wire and through the middle of the wire, and it does heat up. That's why your toaster heats your bread. Your toaster works because that electricity is causing friction, and that friction is a resistor, and that resistor then resists the flow of electricity and heats up as a result of the friction. So a superconductor is normally thought of as pretty close or frictionless. Okay, so a frictionless flow of electrons. Now, it's kind of a pipe dream to find a material that can conduct electricity with no friction, but there have been a number of materials that have been found that if you can cool them down very, very low, then they do act pretty close to frictionless. Okay, so there is a kind of a threshold temperature that each particular material has called the superconducting transition temperature, and that temperature is anything less than that temperature and you get a superconductivity where there's very little friction of that electron going through the material. Okay, so the very highest temperature superconductor was found in the 80s, and that was about 97 Kelvin. Okay, so you remember that that Kelvin is 273 degrees below zero, so that would be like 150 below zero. So that's still really hard to do. To have a material that you can keep 150 degrees below zero is expensive and cumbersome and a nuisance. But this is the highest that anybody has ever found. Okay, so the original ones that were found 100 years ago are 4 Kelvin or 30 Kelvin, so really, really cold. So as materials are developed, it's more possible that you could get a superconductivity. And if you could have a superconducting computer, we're talking about computing times that's mind-blowing. What would normally take days to compute, you could do in seconds. So like computers would really go nuts if you could ever devise this. And so it's a holy grail for a lot of people. So this picture here is a piece of ceramic that you've got liquid nitrogen poured on, and it makes it very, very cold. And then you have a very strong neodymium magnet that's floating on the top of it. So what's happening in a magnet is sending out magnetic fields. There's a magnetic field around that magnet. That piece of ceramic that's very, very cold is exerting, it's called the Meissner effect. And the Meissner effect means that essentially it will not let magnetic field lines into it. So imagine a magnet sitting on a table. The magnetic field lines would go above it in the air and then also below it down into the table. Okay, it doesn't hurt the table at all, but those magnetic lines of force are in the table. Well, if you can cool this down to a certain part, as it becomes very superconductive, it also enables magnets to float. Essentially, the magnetic lines are sitting on top of that thing, and the magnet itself is sitting on top of its magnetic lines of force. So it's pretty cool that if you could use this, okay. If you could use this, I'm sorry, I should have given you this. Here's some of the list of superconductive materials that have been found in the last 100 years. Okay, and you can see that the temperatures there in Kelvin are on the right. So we're looking for higher, higher, higher. The higher we can get, okay, so here's 1995, 1993, 138 Kelvin. That's pretty good. You're getting into cold, but not ridiculously cold. Okay. So here's a picture of a Maglev train. I think this is in China. And it's just a very short path, but it was pretty remarkable because if you can cool the ceramic and then have the bottom of the train actually be really strong magnets, then there's no friction on that train. So if you can imagine a frictionless train, it could go, 500 miles an hour with no problem. You could go from city to city in just a few minutes rather than hours. It would actually be faster to take a train than it would to take a plane in cases like that. So as you develop higher and higher temperature superconductors, the technology around that will be crazy. And so that is my take on ceramics.